Every single rock has a story to tell, a story that can stretch back millions or even billions of years. But how in the world do we read it? In this explainer, we're going to unlock the secrets of geological time and find out about the incredible methods scientists use to read Earth's massive history, a history that's written directly in stone.
So that's the central mystery, isn't it? I mean, you can pick up a rock from pretty much anywhere on Earth, but how can you possibly know if it formed 1,000 years ago or a billion? How do we get these silent stones to tell us the story of our planet? Well, let's dive in and find out.
I think the best way to think about this is like a giant detective story. Seriously, geologists are the investigators, and the rocks themselves, they hold all the clues. Our mission today is to figure out how these detectives piece all that evidence together to solve the planet's oldest mystery, the mystery of time itself.
All right, so our geological detectives start with their very first and most fundamental clue, the rock layers. This method is all about figuring out the sequence of events. It's not going to give you a precise date, but it'll tell you what happened first. This is called relative dating.
It really just comes down to comparison. With relative dating, a scientist can look at two layers of rock and say with total confidence, okay, this one is older than that one. And that is the essential first step to building a timeline, long before you have any specific years to put on it.
This whole thing rests on a really foundational rule, the law of superposition. And it's an incredibly simple but super powerful idea. Basically, if the layers haven't been all jumbled up by something like an earthquake, the stuff on the bottom got there first and the stuff on the top got there last.
It's a brilliantly simple concept, right? Just think about a laundry basket. The shirt you threw in on Monday is definitely going to be buried under the one you threw in on Wednesday. Simple. Rock layers work the exact same way. The oldest stuff is at the bottom.
But the layers themselves hold another amazing clue. Detectives look for something specific hidden right inside them. Fossils. These preserved bits of ancient life act like unique fingerprints, helping to identify specific moments in time.
Now, not all fossils are created equal when it comes to dating. The most useful ones are called index fossils. An ideal index fossil comes from a creature that existed for a pretty short period of time, geologically speaking, but lived all over the world. So if you find that same fossil in Africa and in North America, you know those two rock layers formed at roughly the same time.
But what if you need more than just older or younger? What if you need a number? For that, our detectives turn to their second, super high-tech tool, a natural clock hidden inside the atoms of the rock itself. This is what we call absolute dating.
This is where we go from just a sequence of events to like a specific calendar date. Absolute dating gives us a real number, like 65 million years old, by measuring the breakdown of radioactive elements that are naturally trapped inside minerals when a rock first forms.
And the reason this method works is because of a process called radioactive decay. See, certain atoms are just naturally unstable. Over time, they spontaneously change into a more stable form. And here's the most important part. They do this at a perfectly predictable, totally measurable rate. It is nature's most reliable clock.
So the unit of measurement for this atomic clock is the half-life. This is just the time it takes for exactly half of the original unstable parent atoms to decay into their new, stable daughter atoms. And the scales here are, well, they're mind-boggling. The half-life of uranium-238, for example, is 4.5 billion years. That's about the age of the Earth itself. So here's how it works. A rock first forms, and it has a certain amount of these parent atoms locked inside. As time goes by, they start to decay into daughter atoms. So scientists take a sample and they measure the ratio of parent atoms to daughter atoms. And since they know the half-life, they can calculate exactly how long that decay process has been going on. It's a really brilliant piece of chemical detective work.
Okay, let's actually visualize this so it makes sense. Imagine a rock has just formed. Right now, at time 0, it contains 100% parent atoms. The atomic clock has officially started ticking.
Now, let's fast forward. After one half-life has gone by, exactly half of those parent atoms have decayed. So the rock now contains a perfect 50-50 mix of parent and daughter atoms. When scientists find this ratio, they know one half-life has passed.
And after 2 half-lives, well, half of the remaining parent atoms decay, which leaves just 25% of the original. This predictable progression is exactly what allows scientists to date incredibly ancient rocks with some amazing accuracy.
Okay, so we have two really powerful tools,
relative dating for the sequence, and absolute dating for the specific numbers. But the real magic happens when our geological detectives use them together.
This chart just sums it all up perfectly. Relative dating uses layers and fossils to ask, is it older or younger, and gives us a sequence. Absolute dating uses radioactive decay to ask, how many years old is it, and gives us a hard number. They answer different questions, and they are both absolutely vital.
But here's a key detail you need to know. Absolute dating is most reliable on what are called igneous rocks. That's the kind that form when lava or magma cools down. And why is that? Because that cooling process locks the original parent atoms in place, and it basically sets the atomic clock to 0.
So what about sedimentary rocks? You know, the ones where we find all the cool fossils? Well, this is where the two methods combine perfectly. Scientists use relative dating to see that a fossil layer is, say, squished between two layers of volcanic ash. They can then get an absolute date for those ash layers, which means they know the fossil has to be somewhere between those two dates. It's just a perfect partnership. So after all this detective work, you might be asking, what's the point? Why does knowing the age of some random rock even matter? Well, because cracking this code unlocks the story of our own planet.
Dating rocks lets us build a complete timeline of Earth's history. We can pinpoint the moment life first appeared, we can track the planet's dramatic climate shifts over billions of years, and we can understand the timing of huge catastrophic events, from massive volcanic eruptions to the asteroid impact that wiped out the dinosaurs. I mean, without this knowledge, our planet's past would just be a total mystery.
And this really brings us to the core idea. Rocks aren't just these inanimate objects lying around. They're archives. They are the most detailed, the most reliable, and the most ancient history books we will ever get to read.
So I'll leave you with a final thought to chew on. Why is it so crucial for scientists to have both of these toolkits? Why can't they just figure out Earth's age using only the sequence of layers, or just the atomic clock? The answer, as we've seen, lies in how these clues work together to tell the planet's complete story.